Topic 3, particle model of matter. So as with all the other packs, we're starting with the student checklist. You need to make sure that you have completed all the student checklists for the previous packs, gone through them with the things that we've gone through to RAG rated red, amber, green. Red if you think that you have no idea about that particular topic. Amber if you know some of it, and green if you're feeling confident that you've mastered that particular part of each topic. And this checklist you complete after you have completed marking this pack. As with all the packs, page 2, there are some facts that you need to know and some processes that you need to be able to carry out. For example, to recall and apply the density equation. Okay, so lesson 1 is about density and states of matter. And in the first task, you had to draw the particle model representation of a solid, liquid and gas. Use no more than 16 particles for each. Okay, so a solid, the particles are touching. They're regularly arranged in rows and columns. Because the particles do not move around, they simply vibrate around an equilibrium point, and they're all joined together by strong intermolecular forces with strong force of attraction. In a liquid, and there are 16 of these particles, they're all the same size and shape. In a liquid, the particles are still close together. 2, 3, 4, 5, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So they're in an irregular shape, but still close together in a liquid. So there is still some force of attraction, some intermolecular force between the particles. But the particles can now move around each other. And then finally, in a gas, the particles are all far apart. There are no longer any bonds between the particles. They're all far apart. They're moving randomly in all directions at a variety of speeds. But we still have the same number of particles, and the particles are all still the same size and shape. So we needed to complete these sentences. We say that the particles of a substance in each state are the same. This is possibly the most important thing to realize. First of all, it's the main mistake that most people make. So for example, when something boils, goes from liquid to gas, people often say that the particles boil, but you have to understand the particles do not change. They always remain the same size, the same shape. It's just how they are arranged and the way that they are moving that changes. So the particles in each state are the same, only the arrangement and the energy store in each particle change. So the particles in the gas are moving quickly in all directions, so there's a lot of kinetic energy. The next thing you needed to do was to add some words to go along with your pictures. To explain, and there's a number of things you need to explain: the structure of how the particles are arranged and their motion, and you need to say why it has this arrangement. Okay, so in a solid we have a regular arrangement. What I want you to do is to, once this is complete, pause the video, check what you've written, make sure you make any corrections in green pen. So make sure that you have checked your answers, what you've written in here. If you've missed anything or you need to make any corrections, do so in green pen. So the solids, we have a regular arrangement. Particles are close together. The particles don't move, they only vibrate around a fixed position. And this happens because the particles have very strong force of attraction between them. And the particles themselves have got very little energy. They're only vibrating, they're not moving quickly. So they tend to stay in this regular arrangement. When we have the liquid, the particles are still close together, but now they can move around each other, and we have an irregular structure. In this case, there are weaker forces of attraction, and the particles have got slightly more energy than in the case with the solid. And then finally we have the gas. Here there is no structure, the particles are far apart, and they're moving quickly, randomly in all directions at a range of speeds. There's almost no force of attraction between the particles, and the particles have got much more energy. Okay, moving on to page 2. We're now looking at this term called density. And density is telling us how many particles are crammed into a single piece of space. So we're asked these two questions: explain which state of matter is the most dense and which state of matter is the least dense. So usually solids are the most dense. The particles are very close together because of the strong force of attraction between the particles. And they're close together, which means that all the particles are in a relatively small space, which is what we saw in this little picture here. I say usually because there is one exception that we know of, that we know very well, which is water. Water is very unusual in that the solid form of water, ice, is actually less dense than the liquid form, but that's very unusual. For most things, the solid state of matter is the most dense. Gas is the least dense state of matter. That's because the particles are far apart. So you've got the same number of particles here, but it's taking up a very much greater space than in the solid or the liquid. And the gas particles move apart, far apart, and they fill whatever container they are in. So we can talk about density in terms of how many particles there are in a particular space. And it's defined as the mass per unit volume of a substance. How many kilograms of a substance do we have in a particular amount of space? And you can calculate it using this equation, which you need to learn. So we can say that density is equal to mass divided by volume. And I'm going to write that in symbols. And the symbol for density is this symbol. It looks like a P. It's called rho. It looks like a P. So this is density is equal to mass divided by volume. Volume typically measured in meters cubed or centimeters cubed, and the mass is measured in kilograms or grams. So the symbol for density is rho, and it's measured in kilograms per meter cubed, or in some questions you might get grams per centimeter cubed. The symbol for mass is little m, measured in kilograms, or in some questions you'll be given in grams, and the symbol for volume is V, measured in meters cubed, and again in some questions you might be given centimeters cubed. The next task, you had to rearrange the equation. So we have density equals mass times divided by volume. So that gives me that mass is equal to density multiplied by volume. Mass has been divided by volume here, so to get rid of the divide by volume bit, I need to do the opposite. That's multiplied by volume on both sides. So mass is equal to density times volume. If I needed to calculate the volume, then what I've got is the volume is equal to mass divided by density, because I need to first of all multiply by volume and then divide by density. So that gives me volume is equal to mass divided by density. So just make sure, pause the video, check your answers. And now you have to do some calculations. And as always with calculations, you must show all 4 steps. So for each question, what's most important is that you check that you have all 4 steps: writing the numbers, writing the equation, putting the numbers in the equation, and then finally doing the calculation. In question 3, you'll notice that I've given 2 answers, and this is because we could either choose to keep the lengths in centimeters, which gives us a volume in centimeters cubed. In that case, we would need to change the mass into grams, or we could change the volume into meters cubed, and we end up with units of kilograms per meter cubed, 1875, or grams per centimeter cubed. Either of those would be acceptable. Now, in the next part, we're looking at ways that we could try and determine the density of different types of objects. In each case, we need to work out how would we measure the volume and how would we measure the mass. So if we have a regular object, we need to measure the lengths of the sides. We might use a ruler or a micrometer or a vernier calipers. Vernier calipers look like this, and the reason why they use them is they allow us to make measurements of objects that are much smaller, but also we can measure things like the diameter of objects as well as just lengths. So these are vernier calipers. We could use those, or a micrometer or a ruler. And then we calculate the volume by doing, for example, for a cuboid, length times height times width. To calculate the mass, we place the object on a balance that's been zeroed and we record the reading. If we have an irregular solid, it's not going to work to try measuring all the lengths of the different sides of this object. So what we do in this case is we fill a Eureka can with liquid, typically water, and we carefully add the object, and so long as the liquid has been filled up to the spout that's on the Eureka can, as we add the object, that will displace some of the water, which will spill out and be captured in this measuring cylinder. We can then use the measuring cylinder to record the volume of the liquid that's come from the Eureka can, and that will equal the volume of the object. If the object floats, you need to be careful to make sure that you've held the object underneath the water. Once again, for the mass, we simply need to place the object on a zero balance to record the reading. And then finally, if we have a liquid, to measure the mass, we would place the measuring cylinder on a balance and then zero the balance, then add the liquid to be able to measure the mass. To measure the volume, we read this from the measuring cylinder, but liquids like water inside a measuring cylinder, the top of the liquid is usually not straight, it's curved, and you need to read the number that corresponds to the bottom of this curve, which is called a meniscus. Once again, pause the video, make sure that everything is correct, and then move on to try the question on the next page. So we're told this is a measuring cylinder. A cylinder has been placed on a mass balance. The balance was zeroed and then oil was poured in. Calculate the density of the cooking oil. So we need to read the measurements from this experimental setup. So we can say that first of all, the mass is equal to 10.8 grams. That's from reading on the balance. And we can see that the volume is equal to 10, 11, 12, and the units are milliliters, 12 milliliters. Now 1 milliliter is equal to 1 centimeter cubed. So that means our volume is 12 centimeters cubed. Density is equal to mass divided by volume. So that gives me that the density is 10.8 divided by 12. And I'll pop that into my calculator. And I get an answer of the density is equal to 0.9 grams per centimeter cubed. If you had chosen to change it into kilograms per meter cubed, then we would have had the mass divided by volume is that would be 900 kilograms per centimeter cubed.